May seem a little bit off topic, but we're going to start doing some summations. Deal with some sums. Integration and summation are very tightly tied together. Actually, the formula for integration involves a sum and a limit. Because if you remember, we keep talking about the area under the curve, and we're like, dude, can't we call this thing from like the left to the right? And we just make some freaking rectangles, and we can just add up the area of those rectangles. That's a sum. We're going to add areas of rectangles. But in order for us to do it, we got to be able to read the damn notation. If you're a student like myself, I really don't think I'd seen any sums. Maybe I'd seen the symbol, but I hadn't really played around with it until I got to calculus. And you're going to see it more in Calc 2. You'll see it more as you progress. It just becomes used more. So let's make sure that we kind of know what the hell's going on. So this is a little bit of almost of a review. In case you missed out in college algebra, maybe you were asleep that day. There it is. We got this thing. It's a sum. It says add them up. The summation symbol. Sigma. Sigma. Capital sigma. I know I get this a lot. They're like, no, sigma looks different. Nah, but that's the capital, right? It's the capital. So let's talk about what else is going on in here. This is called our index. It's telling us where to start. It's like where to start. And then up here, this is where the index ends. And this is our formula. This is our formula, whatever it might be, for the ith term. Ith term. Okay. Let's just see an example of it written another way. So it'd be like, all right. I is equal to 1 up to 3 of, and let's put in something crazy. Let's get nutty. Let's call it I squared. Well, this is telling us down here, start at 1. So pop in 1 squared. Pop in 1 squared. So we're like, all right, put in 1. All right, plus, we go to our next 1 squared. What's the next number after 1? Now these are what we call finite or discrete values. No fractions. 1, 2, 3, 4, 5. No fractions. None of that bullshit. Whole numbers. So then we go with 2. And then we go to our next one. Well, we got to square our next thingy. What comes after 2? And that's 3. But 3 is where we end. This is our end point. So it says, oh, you're just supposed to take the numbers 1, 2, and 3, square them, and add them up. It's a sum of squares. Well, there we go. We just used our little index to do it. And I don't know, was this 1 plus 4 plus 9? I don't know, was it 14? Neat. Cool. But what we care about is how do we write this shit? Let's do a couple more examples. Maybe we play around with this. Let's say I is equal to 1 up to 7 of f of I. You're like, oh shit, what the hell is going on? There's barely any numbers. There's more symbols in here. But I just want you to see how this is going to work. We're like, there's some function. Usually the function will be like x squared minus 3 or some shit like that. You'll actually have something in there. So we're just going to say that this is f of 1 plus f of 2 plus f of 3. And we're going to go all the way up until we get to 7. I don't know what any of this shit means. It's just some random ass function telling you to just plug all the numbers in, start at 1 and go all the way up to 7. Add those suckers up. Let's go. Let's do this one here. Let's take the sum as I is equal to 1 on up to, let's just go to 2 this time, and we're going to call it I over I plus 2. So there's actually a function, right? There's something going on there. There's some rational function happening. So we're going to say, all right, let's write our first term in. So anywhere we see an I, we're going to plug in a 1 for our first term. So let's go plug that 1 in. 1 and 1. All right, cool. Well, we got more to do. Let's go to our next one. We write everything in. And now we're going to replace it. What comes after 1? Damn straight 2. And we look and we're like, well, that's as far as we needed to go. Oh, we only had to do a couple. No biggie. So if we were to clean this up, you get 1/3 plus 2/4, which is 1/2, which is equal to 5/6. There we go. Who cares what the number was? All you need to be paying attention to here is how can you write this like this? Messing around with our frickin' sums. Okay. Now, let's do just one last one. We'll go back to what we're after here. Let's look at this third one. Let's do it this way. Let's say I is equal to 3, and we're going to go up to 5. And this time we're going to say it's -1 to the I times I. Oh, shit. Well, this time we're not starting at 1. We're starting at 3, because the bottom tells us where to begin. If it told you 18 trillion, you're like, shit, I started 18 trillion. And of course, and what's up above, it's got to at least be the same size, or if not bigger. If not, it's a bunch of freaking nonsense. So let's write our stuff in. We get our -1 raised to a power, and that power is going to be 3. And it says multiplied by 3. All right. Next one, we got -1 raised to a power. The number that comes after 3 is 4, so we'll do that. And now we'll add it to our last term, so we're only going to 5, and that's -1 raised to some sort of power, which is 5, times 5. And this is a game we play. -1's raised to powers. If it's an odd power, it's going to remain negative. If it's an even power, it's going to remain positive. This is going to be something you'll play around a lot with. Your past peers are freaking studs with this stuff, because they're having to deal with this quite a lot. So this looks to be -4. There we go. Just playing around a little bit with our new add 'em up notation. Now we got a bunch of rules that happen with them too. We got rules to these sums, but they look like the limit laws almost. They almost look like the limit laws, where it's like if you got the limit of 2 things when you're adding them up, you can just break them apart and just add them. If you had a subtractions in the center, you could just break them into 2 pieces and just do them individually. That's what you do with limits and derivatives and antiderivatives and sums and numbers and algebra. You already know these rules. It's just getting used to this effed up notation. We also have that if you had a constant, something that's going along for the ride in all of them, you could just yank it out to the front and just leave that piece there. And then our last one, if you just had a constant written in there, this one says K instead of I stole it from a different book. And we're going to go up 5 times, and our constant is 3. That's saying you're going to write 3 plus 3 plus 3 plus 3 5 times. Because there's no I in there. There's no K in there. There's nothing to plug into. So it's just saying, write 3. You're like 3. And then how many do we have? There's 5 of them. So this ends up being 3 times 5. Or your C times your N. Your C times your N. So that's your little constant value rule. It's a little funky. That's where most students screw shit up on these. So let's play a couple games and we'll get out of here and we'll start using it. Let's see this first little game that we can play. Let's take this and just mess around. Go, all right, I is equal to 1. Let's take that thing up to, we'll write it up to n now. We'll look at this. 3i minus I squared. And let's use our new rules to break this thing up into something a little bit more simple. So this tells us that, well, maybe we first step in, we just break up the minus sign. Now, if you want to do all of it all at once, you go right ahead. I'm going to do 2 steps instead of just doing 1. So we get to right there, and it says we can square, and now the last game is we can take this 3 and now yank that to the outside. And now we just have simple multiplications. Of 3 times our sums. And we break it down in these ways. We're doing this for a purpose. I don't know how much you're going to like this purpose, but you're going to have this. This is going to be a reason why you want to know it. Here we go, I plus 4. I'm about to show you. I know this is a little bit of a longer one, but we could say that I is 1 to 3 of I plus I is equal to 1 of 3 of just the number 4. We're going to want to start evaluating these and finding out what the answers might be by taking them to certain numbers. Like this here can be solved by using formulas, even if this was taken all the way up to the 300th. We have formulas that will quickly happen. Instead of writing that shit 300 times, now imagine once we start approaching infinity times, it's going to be a little rough to be able to solve. So do you all have this memorized? Do you remember this? Do you remember your sums? I know that this is from, I believe you need to know this for the SATs. So if you just sum a bunch of numbers, like 1 plus 2 plus 3 plus dot dot dot, the sum of all of the natural numbers, this is actually equal to whatever the index was, or the end index value, times itself plus 1 all over 2. So here's 1. And we're going to play around with these in the next one. So I'll bring it back, and then we got a couple more. Now what's the sum of squares formula? And the sum of squares formula, that 1 squared plus 2 squared plus 3 squared plus dot dot dot, this also has a formula, which is called n times n plus 1 times 2n plus 1 all over 6. There's another. And lastly but not leastly, what are we going to do when we have a sum of cubes? A sum of cubes, and the sum of cubes would look like this, but like 1 cube plus 2 cube plus 3 cube plus dot dot dot. That goes on for frickin' up until our nth, not writing it in. Fortunately, this isn't so bad. It's the same thing as what we got for the sum of our i's, just we square it. So very similar formulas. Is really you only got to memorize 2 and you get the third for free. So the sum of integers up to n is equal to this. The sum of squares of integers up to n is equal to this formula. And the sum of cubes summed up until some value of n will equal this. And in our next one, we will play around with this. We will solve some, and then we'll move into integration.